For some more basic forms of antiderivatives, let's consider exponentials. Two kinds of exponentials will be, first off, our favorite, the natural exponential. The derivative of e to the x would be e to the x. So the derivative does nothing. The antiderivative should do, well, the inverse function of doing nothing, which would be to do nothing. So that lets us know that the antiderivative of e to the x is going to be e to the x plus a c. You can verify this result by differentiating this. For any other exponential, like say a to the x, the derivative would be the same thing but multiply by the natural log of a. So for an antiderivative, it'll be the same exponential, except we are going to divide by the natural log of a. Once again, we'll keep on that plus c. Now, after exponentials, we should probably also talk about trigonometric functions. So for every rule for derivatives, there's going to be a corresponding rule for antiderivatives. If I differentiate the sine of x, I will get the cosine of x. This lets me know that if a function is the cosine of x, then the antiderivative is going to be the sine of x plus a constant. The derivative of the cosine of x is going to be equal to the negative sine of x, which lets me know that if I have the sine of x as a function, the antiderivative is going to be the negative cosine of x plus a constant. You could do this for all 6 different forms of the derivative. So for the tangent, that would be the secant squared of x. Therefore, if you have the secant squared of x, its antiderivative will be the tangent of x plus a constant. For the cotangent of x, that would be the negative cosecant squared of x. So in the event that you have the cosecant squared of x, the antiderivative is going to be the negative cotangent of x plus a constant. The derivative of the secant of x is the secant of x times the tangent of x. So if I give you the function secant of x times tangent of x, then the antiderivative is going to be simply the secant of x plus a constant. And finally, the derivative of the cosecant of x is equal to the negative cosecant of x cotangent of x. So if I give you a function that is the cosecant of x times the cotangent of x, the antiderivative is going to be equal to the negative cosecant of x plus a constant. So basically take any rule for derivatives that exists and rewrite it so that we're taking the antiderivative of this part and we're arriving at this part. Please note the use of minuses. They are in the same spots as where they are for the derivatives. Next up, there is another basic form for the logarithm. And we'll stick with the natural log for this one because there aren't really a whole lot of situations where anything else would show up. The derivative of the natural log of x we know to be 1 over x, which lets us know that if you are given f of x is equal to 1 over x, this is not a situation where you would use the power rule. This will actually wind up being the natural log of, for a surprising result, it winds up being the natural log of the absolute value of x. And for this I'd like to explain. If you consider the natural log of the absolute value of x, this is going to be defined piecewise based on the definition of what the absolute value is. So this will be the natural log of x, provided that x is greater than 0. But if x is less than 0, it's going to be the natural log of negative x. Input something negative, you can turn it into a positive by multiplying by an additional negative. If I were to differentiate this function, the natural log of the absolute value of x, and we go piecewise once again, the natural log of x for the first part would just give us 1 over x, for x being greater than 0. The derivative of the natural log of negative x would be 1 over negative x times the derivative of negative x according to the chain rule. You'll notice that these, if you cancel out the negatives, will simply be 1 over x once again. So antiderivative of 1 over x is going to be the natural log of the absolute value of x. Finally, there are 2 more basic forms that you should know for the inverse trig functions. Those are going to be if f of x is equal to 1 over the square root of 1 minus x squared, then the corresponding antiderivative is going to be the arcsine of x plus a constant. And if you happen to see 1 over 1 plus x squared, then the antiderivative of that is going to be the arctangent of x. Now, we're not going to put too much emphasis on these particular forms because there will be a technique that you'll learn in Calculus 2 for exactly how to deal with things of this nature. So, quick example pertaining to all of the basic forms that we've just seen. Let's consider the function f of x is equal to, let's do 4 raised to the x power minus the secant squared of x plus 1 over 1 plus x squared. Good variety in here. So the antiderivative of this function, if we go term by term, 4 to the x would be considered an exponential. Exponential is going to be the same exponential divided by the natural log of the base. Derivative says multiply by the natural log of the base, so the antiderivative we divide by the natural log of the base, minus the function whose derivative is secant squared of x. That would be the tangent of x, plus the function whose derivative is 1 over 1 plus x squared. That would be the arctangent of x. And to keep it as generic as possible, we of course will tag on our plus c.